Okay, let's start. So the topic of today's video will be solution of PDE of the form f xyz comma pq is equal to 0. Means we'll be solving the PDE involving the partial derivatives, first order partial derivatives, small p and small q, right? So the aim of the Charpit method is to solve a type of PDE. Consider PDE of the type f x y z p comma q equal to 0. Let it be equation number 1. Right, this partial differential equation is involving the first order partial derivatives small p and small q, right, as we did in Lagrange's form equation. That was capital P small p plus capital Q small q equal to capital R, right, and that differential equation was also involving small p and small q, right. But this is the more generalized form. In this PDE, we can have some powers of P and Q also. Means you are not restricted to solve the PDE of first order and first degree. This Charpit method allows us to solve an equation of the form involving P and Q and P raised to the power 2 or 3, anything, right? Okay. So this is what we are finding the solution for, and to solve this equation we seek a relation of the form, let me say capital F x y z p comma q equal to 0. This is my equation number 2, right? To find small p and small q, and use dz is equal to del z over del x dx plus del z over del y dy, right, to get the complete integral. What does it mean actually? I am given the PDE of this form containing P and Q, right? Okay. Then I need another relation of this form. Let me call it capital F, okay, and that will also involve this P and Q, right? I will solve these two first and second for P and Q. My main motive is to obtain small p and small q in terms of x, y, and z, right? Then after obtaining small p and small q, after solving these two equations first and second, right, I will plug in those small p and small q here. Actually this is small p. If you see that, this is small p, right, and this is a small q, okay. Then I will substitute those p and q here and I will integrate this. Then I will be obtaining z in terms of x and y, and that is my aim, to obtain z, the complete integral for this PDE, right? Okay, so right, differentiating this equation number 1 with respect to x partially, right? Okay, differentiate equation number 1 with respect to x, right, partially obviously, and notice that this f, you may consider it as a function of f, function f depending on the variables x, y, z, p, q, right? And I think it will be better if I draw a tree here for this f. Let me draw it here. Okay, I will rub it f, and see that f is a function of x, y, z, p, q, right? Okay, so f x y z p q, right? This is what that is obvious from this equation number 1. Okay, now you know that z is also a function of x and y. This is obvious because you are going to find the complete integral, that is z in terms of x and y. You know that z is always a function of x and y, okay. And again, what is this small p? This is small p is actually del z over del x, the partial derivative of z with respect to x, and that may contain x or y. So again, p is maybe a function of x and y, right? Similarly, q is a function of x and y. right? Because p and q are first order partial derivatives, and these derivatives may involve small x and small y. That's why I am writing here xy. Okay, that's fine. Now what do I want? I want differentiation of this first, that is small f, with respect to x. And look in this diagram, how many paths are there to reach x starting from f? One path is this path, this one, right? And second is this path, third is this one, and fourth path is this path, up to here and then here. I have four paths, and I will write this derivative using that tree, right? The first path is f2x, that will be del f over del x, del f over del x, then plus second path del f by del z by del x, del f by del x and del z by del x, but this del z by del x is actually denoted by p, so I'm writing it as p, small p. Okay, a small p. And third path is del f by del p, del f by del p, and then del p by del x, right? Plus last path del f by del q and del q by del x, del f by del q and del q by del x, right? And is equal to differentiation of 0 will be 0. Okay, so this is equation number let me call it 3, third equation, right? Similarly, differentiating equation number 2 with respect to x, let me add it here, differentiating first and second with respect to x. Okay, now the treating the function f same way, then I will be getting something like, see that capital F is also function of x, y, z, p, q, so then you can replace this small f by capital F, and following the same process you can write this equation, right? So think capital F in place of small x. Your equation will be del f over del x plus del f over del x p plus del f over del p over del x plus del f over del q and del q over del x equal to 0. This is equation number 4, right? Okay. Similarly, differentiating first and second with respect to y now. Okay, differentiating again first and second with respect to y, right? Now I have to reach y starting from the small f, and see the path. This is the path. First path, these straight lines, I'm not retracing them. This path del f by del y, and second path is del f by del z by del y. Third path del f by del p by del y, del f by del q by del y, in the same manner as we did here. So I'll be getting del f over del y plus del f over del, oh, this should be x, this should be z, del f over del z, sorry, small correction, del z. Okay, now del f over del z and then del z over del y. Del z over del y is actually a small q. Third path del f over del p and then del p over del y. Del f over del p and del p over del y, right? Fourth term del f over del q and then del q over del y equal to 0. This is my equation number 5, right? And similarly doing the same thing for capital F. I mean, you can imagine capital F here and writing the same derivative, del f over del y plus del f over del z q del f over del p over del y. I'm right or wrong? This is, so differentiating with respect to, no, this should be x, oh y, right, y. Okay, plus del f over del q and del q over del y equal to 0. Okay, sixth. So I've got 4 equations, right? And I have to do something to eliminate. I think if you focus on this term, means this term, this one and this one, these two terms can be cancelled out if I multiply this by del f over del p, means third multiplied by del f by del p and fourth multiplied by del f over del p small, right? Okay, let me rub this. This is not needed now. And see, now focus on this term, third term, right? You want to cancel it, so you should multiply this by del capital F over del p and multiply fourth by del small f over del p, right, in order to cancel the third term. Now third multiplied by del capital F over del p minus fourth times del small f over del p. Then I will be getting something like, because this will be cancelled, okay, and I will be getting first, second, fourth term multiplied by this thing, okay, del f over del x plus del f over del z p plus del f over del q over del x, this whole thing multiplied by del f over del p minus, then fourth equation, first, second and fourth term, del f over del x plus del f over del z p plus del f over del q over del x, then multiplied by del small f over del p is equal to 0. Okay, fine, right. And if I write it as right, so if I simplify and rearrange the terms, means if I take the first term, this first term and this first term written together, or on rearranging this, I will get del f over del x multiplied by del f over del p, fine, minus this first two terms product del f over del p and del f over del x. This is the first term and first term. Then taking the second term, and I think that will be del f over del z, del capital F over del p minus del small f over del p and del capital F over del z multiplied by p, and writing the third term, this term, okay, that will be del f over del q over del x, del f, I think something will be common, del q over del x will be common, yes, del f over del p and minus del f over del p, del capital F over del q, and outside we will have del q over del x, yes, is equal to 0. Yes, so this is my equation number, let me call it 7, equation number 7, okay. And similarly, focusing on the third term of this equation number 5 and 6 and trying to cancel out this third term, I will have to multiply this by del L capital F over del P and the sixth equation by del small f over del P, right? Then I will subtract these two, okay. So fifth multiplied by del capital F over del P minus sixth multiplied by del small f over del P, right? Okay. And then doing the same thing as I did here, I will be getting something like, should I write it directly? We may write it directly, okay, but okay, I think x should be replaced by y, because everywhere we have x, and in these equations where we have y, right, in the denominator, means these things have to be taken care of while writing something directly, okay. And wherever we have small p, right, and we will have small q, because this will be cancelled, so ultimately in the denominator we will be having small q, means you can think like that. If you want to write it directly using equation number 7, you don't want to calculate this, then keep in mind x should be replaced by y and p should be replaced by q, right? And this is an observation I made after seeing this equation 5 and 6, because third term will be cancelled out, right? Then I will be having y in the denominator, z in the denominator, that's fine, and q in the denominator. Means p should be replaced by q and x is replaced by y. If you want to use this relation 7 to write the equation number 8 directly, so I'm writing that directly. Okay, then I will be getting based on these lines del f over del y, here I will have y, del f over del q minus del f over del q and del f over del y. This will be my first term, right? And similarly plus del f del z del f del q minus del f over del q and del capital F over del z, and this should be q, yeah, plus del f over del p del capital F over del q, yeah, minus del f over del q and del capital F over del small p, right? And that this will be del p by del y is equal to 0. Okay, right. Okay, then yes, if you subtract 8th from 7th, then I think this whole term, series term, del f by del q, del f by del p, this is the same present here but with the reverse sign. Series, these two terms, they are same, and this term is similar to this term. Here we have negative sign, positive sign, and outside we will have del q by del x. Del q by del x means, I should write it here, use del q by del x. Actually small q is, what is small q? Small q is del z over del y, that is actually equal to del square z over del x del y, right? And that is equal to del square z over del y del x. That is obvious. In these conditions the second order mixed derivative is equal. Yeah, rather you write del x by del y or del y by del x, that is same. In certain conditions it is not always equal in some cases, but here we will have both these partial derivatives equal. Okay, that is equal to del over del y and del z over del x, and this should be equal to del p over del y, right? So this result means del q over del x is equal to del p over del y should be used here. These two are equal and the inside term is also equal, so after adding them the whole term will cancel out, this last term will cancel out, right? So adding 7th and 8th, add 7th and 8th, so adding them, okay, yes, fp, I will be getting 4 terms, first, second, third, fourth, and this will be completely cancelled, and writing them in some nice way, should I write it as first term should be del, okay, I should start from here. First term will be this term, del f by del this term. First I will write this term, okay. Then second term will be containing del f by del y. This is del f by del y, okay. Second term will be this term, first, second, right? Third term will be del f by del z. This is the term del f by del z. Third term, this is del f by del z, del f by del z. Okay, so I will write first 3 terms. The first term will be after adding them, right, and rearranging them. I don't want to write everything here, right? To do some calculation in your mind. First term will be this term, second I will write this, and third this. Then we will see after the next terms. I will adding 7th and 8th and rearranging them and writing the first term minus del f over del p, and see this is del f over del x, and this capital del f over del x I am writing it as f small x, right? This is another notation to write the partial derivative. It means del capital F over del small x, right? Okay, then writing the second term plus minus del f over del q, and this should be written as capital F y. Okay, now the third term will be the sum of these two terms, and see these two terms, yeah, del f by del z will be taken out common, and inside I will be having minus p del f over del p and the minus q del f over del q, and outside I will be having f z. So I have written 3 terms. Now the fourth term will be del f over del p, this term, let me put a cross here, fourth term, and yeah, this is also del f over del p, this will be my fourth term, right? And my fifth term will be this term, del f by del q term, right? So I'm writing the fourth term first. Taking common, del f by del q will be common inside. I'll be having something like plus del f over del x and plus, no, minus, plus, here we have minus, yes, okay, minus, there is that term, this term, plus p times del f over del z, and outside I will be having del capital F over del p, and similarly the other term will be, right, fifth term from these two, that will be del f over del y plus q times del f over del z f q, and I think all terms are written now, nothing is left because these two terms will cancel out, is equal to 0, right? Okay, or you can see that you see that this equation has dependent variable capital F, right, and the independent variables are small x, small y, small z, small p, and small q. Means capital F is the dependent variable depending on the independent variables x, y, z, p, and q, and that is what you wanted from equation number 2, right? You are thinking in that way that f is depending on all these parameters x, y, z, p, q, right? And if you want to solve this equation, then the solution will be given by this equation. I mean, I have to mention something else here, that in order to write the solution for this, right, let me write the solution first, then auxiliary equations for this, let me write it equation number 9 for 9 are given by dx upon this thing, what is this, minus del f by del p minus, I mean write this small fp, right, then del dy upon this term minus fq, then dz upon, this is the partial derivative with respect to z, will be upon this thing minus p fp minus q fq, then here I will have dp upon fx plus p of z equal to dq upon that ratio del f by del y plus q times del f by del z. Okay, and you can write here del capital F upon 0 because right hand side is 0. And how I have written this, recall that I should write it that here, recall that you what you did for this form, p plus q equal to r. This p was del z over del x and this q was del z over del y is equal to capital R, and this is Lagrange's form, you know that, right? For this, the subsidiary equations are given by dx upon capital P, dy upon capital Q, and dz upon capital R. If you compare this Lagrange's form with this standard form, it is containing more terms and more coefficients, right? Here z is the dependent variable depending on x and y, right? Means two independent variables, so we have three ratios, right? You are familiar with this, how we obtain this, right? And here we have one dependent variable, that is obviously capital F, and but here in spite of having two independent variables, we have 1 2 3 4 5 dependent variables, and those are x, y, z, p, and q, right? So generalizing this auxiliary equation, I have written this, okay, right? It is easy to see. This is dx upon this, dx upon p, dy upon q, and dz upon this r. So dx upon this, dy upon this ratio, dz upon this ratio, dp upon this ratio, dq upon this ratio, and the right hand side is 0, means capital R is 0, so d is f upon 0, right? This is called Charpit's auxiliary equation, and we will be using these equations in order to obtain p and q. Remember that my goal was to obtain small p and small q, and to plug in those p and q here, in order to get the complete integral, right? So my goal is to obtain small p and small q. I will anyhow obtain small p and small q from these 5 ratios, and then I will plug in those small p and small q here, and I will be integrating them to obtain z, right? So in numericals you will be taking this beautiful formula. It is not easy to remember this because these ratios are something complicated. You have to remember this formula in order to perform a numerical, right? So this is the Charpit's method, and it works for all if the PDE is containing the P and Q, right? Not RST. Second order derivatives are not allowed, right? Only first order partial derivatives, and they may be present up to any degree. Means P square is present, fine. P square, Q square, fine. Q to the power anything, that's fine, right? And this allows us to solve a non-linear PDE also, because if in a PDE P square term is present, P square means del z by del x whole square, then it comes in the category of non-linear equation, right? And by using Charpit method we'll be able to solve that non-linear equation also. Okay, so taking numerical for this. Okay, so example number one. So taking the simplest example, obtain solve z is equal to px plus qy is equal to p square plus q square. And if you see this PDE, you can verify that this is a non-linear PDE. And why I'm calling it non-linear, because see these terms, p square is present, q square is present. However, it is first order PDE. This first order partial differential equation means second order derivatives are not present here, means r, s, t and absent, right? So this is the first order PDE, but it is non-linear PDE. So it can only be solved by Charpit's method. Any of the method we did in our previous videos will not work here. That all methods were for linear PDE, right? Okay, so first try to write this in the form of small f, right? I have to write it as a solution here, the small f, right? There is a function of, obviously there is a function of x, y, z, p, q. You can write it as, okay, p, q, and that is equal to, I take all this term here, z minus px minus qy minus p square minus q square. I'm going to write it as 0. This is the relation, this is given, right? And then I have to use this auxiliary equation in order to solve, right? Then I'm using the formula dx upon, see here, del f by del p means differentiate f partially with respect to p, right? Taking p as an independent variable. Del f by del p will be minus x minus 2p, am I right? Yes. Then dy del f by del q, and here we have minus sign also, no? Yeah, then it will become plus. Okay, then del f by del y, del f by del q, sorry, differentiating with respect to q and putting negative sign, I will be getting y plus 2q. Then dz, and dz is given by minus p times fp and minus q times fq, means multiply, you can see like that, multiply this by p and multiply this by q and add them, you will get this, right? So no need to evaluate these derivatives again, you just write the result, means that this result gets multiplied by small p and this result gets multiplied by small q, and then you add them, right? Rather than calculating them again and again, try to write it directly, multiplying it by p, yeah, and it by q, and then adding, I will be getting something like px plus qy plus 2 times p square plus q square, right? Okay, then moving to our fourth ratio, that is dp over this thing, okay, is equal to dp over del f by del x, differentiate with respect to x, that will be, I think, minus p, and plus p times del f over del z, and del f over del z is 1 into 1. Similarly, dq upon del f over del y will be minus q and plus q times del f over del z 1. And you need not to write this because that will produce a f is, if I take this ratio, means this sixth ratio, then that will give me del f df is equal to 0, and on integrating I will be getting capital F equal to constant, and that is obvious, means capital S will represent something, some integral is equal to constant, so no need to write that ratio. Okay, that is obvious. So I'm taking only 5 ratios. So this will give me, means all ratios will be 3 ratios will be same, but the fourth and fifth ratio will give denominator 0, right? So, or dx upon x plus 2p, dy upon y plus 2q, dz upon px plus qy plus twice of p square plus q square, and here I will have dp over 0 and dq over 0. Now I am interested in finding small p and small q, and then plug in that dz equal to p dx plus q dy, right? So I have to take these two, means taking third ratio, taking third, not third, fourth ratio, right? Taking fourth ratio equal to any ratio, means to equal to any ratio equal to any of them, suppose dx by x plus 2p, right? Then I will be getting dp is equal to 0, because 0 gets multiplied here, that will give me 0. Okay, then I'm integrating both sides, I will be getting p is equal to small a, right? Where small is a constant. I am not writing that. The small is a constant of integration. Okay. Similarly, taking fifth ratio equal to any ratio, let me take again first, then I will be getting dq is equal to 0, and that will produce q is equal to small b, right? So I have got the small p and the small q, and I will plug this small p and small q in my equation. Then dz is equal to p dx plus q dy, or dz is equal to a dx plus b dy. One second, if I plug this p is equal to a here, then it will be ax plus a square, and then this will be quadratic in q, right? And what about if I substitute, then dz equal to p dx, p is equal to a, yes. If I integrate it, I will be getting z is equal to ax plus by plus some constant. Okay, right. Then I can compare these two equations, and that is also possible. And but if I substitute p is equal to a here, ax plus qy, and then a square plus q square, can I obtain q from there? That will be in terms of y. Okay, that's fine, leave that. And dz equal to a dx plus b dy, then on integrating I will be getting z is equal to ax plus by plus some another constant, let it be capital A, right? And let it be equation number, no, this is 1 and this is 2, right? And this is also value of z, right? But it is containing 3 arbitrary constant, and I can remove one constant by equating second and first, because this is also z and this is also z. Compare first and second. If I compare first and second, then z is equal to first is this. Okay, then I will get a is equal to p and b is equal to q, that are verified here, right? And obviously this capital A should be equal to p square plus q square, right? Therefore solution is z is equal to ax plus by plus, sorry, capital A equal to p square plus q square, no. And okay, fine. What is p? P is small a square plus b square, right? Using these two, a square plus b square. This is a complete solution, right? Okay. because I had first order PDE, and that's why only two constants, right? This is my solution, and you can see that the solution is can be merely obtained by replacing small p by small a and small q by small b. If you put p is equal to a and q is equal to b, then you will get the solution, and that is also called Clairaut's form, right? The equation of partial differential equation of the form z is equal to px plus qy plus f of pq. F of pq means function of pq. Then the solution is always z is equal to ax plus by plus f of ab. This is called Clairaut's equation, right? Z is equal to px plus qy plus f pq. The solution is z is equal to ax plus by plus fab, right? You can write the solution directly, right? If I take here in place of p square plus q square, if I write log of pq, log pq, then the solution will be z is equal to ax plus by plus log ab. If I write z is equal to px plus qy is equal to sine of p square plus q square, the answer will be z is equal to ax plus by plus sine of a square plus b square. Means p is replaced by a and q is replaced by b, and that is called Clairaut's equation. Okay, so I will take another example. Okay, example number 2, and that is solve z is equal to 1 over p plus 1 over q, right? Okay, so again, if you simplify this, you will get here. If you simplify this, you will be getting p q z is equal to p plus q, then minus p minus q equal to 0, and let me take it f, right? Okay, right. This is f, and again you see that again this is the first order PDE because p and q are present, and but the product pq is present, so it will go into the category of non-linear equation, right? And then applying Charpit's Lagrange's equation, dx upon, and be careful here, dx upon del f minus of del f over del p, right? Okay, should I write the formula first? Minus of del f over del p, and dy over minus of del f over del q, and dz over multiply this by p and this by q, and you will get this. Okay, and d then dp upon, here I had what I had, p f z plus fx, and dq over q f z plus fi. So remember these 5 ratios. Okay, or I will get dx over minus of del f over del p, differentiate this with respect to small p, I will be getting something like 1 minus 1, then minus minus become plus, minus q z dy, and this with respect to 1 minus p z dz over, then multiply this by p and this by q, and then add, I will get p plus q, right? pqz, no, pqz, qpz, they will be cancelled, 2 pqz. Okay, this is the third term, right? Then dp over p times, yes, p times del f over del z, that will be pq, plus del f over del x, no, 0, dq over q times del f over del z, again the same thing, pq, and then del f over del y is 0. Okay, right? Or I can write it as, or dx upon 1 minus qz is equal to dy upon 1 minus pz dz upon p plus q minus 2 pqz is equal to dp over p square q and dq over pq square, right? Okay, so I am interested in finding a small p and a small q, so I should take these 2 ratios, and okay, then I will get something, a relation of p and q, relation between p and q. So taking last 2 ratios, taking dp over p square q and dq over pq square, and then cancelling PQ from both sides, I will be getting dP over P is equal to dQ over Q. Then on integration both sides, I will be getting log P is equal to log Q plus log C, constant of integration, and that will produce P is equal to QC, right? Implies P is equal to CQ on integration, obviously. Okay, and let me put a box on this relation. Is P is equal to CQ. This time we have a relation in terms of P and Q, and what do we need? We need to find P and Q in terms of X, Y, and Z, and then we'll plug P and Q and dz equal to P dx plus Q dy. But here I am having a relation, and in order to find P and Q explicitly, I should solve these two. This one, that will be number 1 and number 2. Plugging the value of P in equation number 1. Substitute P is equal to CQ in equation number 1. Okay. Then if I put P is equal to CQ here, CQ plus Q, then 1 by Q will be common. Okay. Z is equal to 1 by Q will be common, and inside bracket I will be having 1 by C plus 1, and I have to find Q in terms of Z, and I will be getting implies Q is equal to C Z C plus 1. This will be my Q explicitly in terms of Z, right? You need to find P and Q in terms of Z X Y, right? Okay, so this is my Q. I will be using this and plugging this Q here. If I put this Q here, then I will get P in terms of Z. Then using equation number 2 again, P is equal to C times of Q, and C times of Q, C will be cancelled out. I will be getting C plus 1 upon Z. So I am having P and Q explicitly in terms of X, Y, and Z, right? Now I will put P and Q in my equation, dz equal to P dx plus Q dy, right? I have to rub this. Okay, now using dz equal to P dx plus Q dy, then dz equal to the value of P, C plus 1 over Z dx, the value of Q, C plus 1 over Cz dy. Then you will see that Z can be taken here. This will give me Z dz is equal to C plus 1 dx, and then C plus 1 dy over C, right? Now you can write it as 1 plus 1 over C. It's fine. C plus 1 over C. Then integrate. Okay, I will get Z square by 2 is equal to C plus 1 will be taken common, and inside bracket I will be having X, here I will be having Y over C, and then another constant capital A. So this will be the solution. Multiply 2 here, right? This will be the solution, right? Or you can multiply this 2 here or take a square root of it. Okay, then that is containing only 2 arbitrary constants. This is the solution. Complete integral is solution, right? So, right, let me take another example. Example number 3. Solve Q square equal to 2P, right? Then here F should be equal to Q square minus 2P equal to 0, right? Again, this is a non-linear equation because containing the term like Q square. Okay, then I am trying to write this equation directly, using this formula, and I think I should be writing, okay, dx upon minus del f by del p, and that will give me minus del f by del p, that will be 2. It will become plus minus 2. Okay, dy upon minus of del f by del q, that will give me minus of 2q. Okay, then dz upon p dx plus q dy, right? So p 2p plus minus 2p 2q square, if I'm not wrong, multiplying this by p and this by q and then adding them, right? And dp over, see this p times del f by del z plus del f by del x, and since it is not containing x and z, then everything will be 0. Similarly dq over 0, and that is a good thing, right? Okay, so taking dp over 0 equal to any ratio, this ratio, any of these three, I will be getting p is equal to some constant a, right? And okay, and if I put p is equal to here, rather than taking dq equal to 0 and now integrating, I will obtain q is equal to b. Then I have to do comparison with this result as I did in example number 1. Then rather you substitute p is equal to a in this here. Let me call it equation number 1. Substitute p is equal to a in equation number 1. Then you will be getting what? Q is equal to how much? Q is equal to q square equal to 2a, right? Then it will be q is equal to square root, or should I take dq is equal to 0? Then I will get rid of that square root, right? Q is equal to a, then putting q is equal to a here, I will be getting 2p is equal to a square, and then p is equal to how much? A square over 2, right? This is what I need. I don't want a square root. Okay, then using dz is equal to p dx plus q dy and plugging these values, or dz is equal to p value of p a square by 2 dx plus a dy, and then integrating it, I will obtain z is equal to a square x by 2 a y plus b. B is a new constant of integration, right? Every time you perform an integration, you will write a constant of integration is solution, right? So this is a solution for example number 3, and you can see that you have to remember this Charpit's subsidiary equation in order to find the solution of this non-linear PDE containing only partial derivatives of first order p and q. So we'll perform maybe some another examples in next video. For this video, thank you so much.